Welcome to today's Explainer. We're unpacking a really fascinating developer update today. It's all about using Haskell and the Typst typesetting system, which, by the way, is just a fantastic modern alternative to LaTeX, to generate these beautifully indexed ebooks. Seriously, if you've ever found yourself totally lost in a massive digital document, just wishing for a smart, automated way to find exactly what you're looking for, well, you're in the right place. Today, we're diving into a real-world programming journal, and we're going to see how raw code gets translated into the practical logic of document formatting. So we're jumping right into part 139 of an ongoing series called Notes on Haskell-Programming. It's by a developer named Ang, and honestly, 139 parts into a programming journal, you just know this developer is deeply, almost heroically invested in this project. Specifically, we're zeroing in on updates to a console tool called XS2 ebook. This tool takes text and converts it into properly formatted ebooks, but Ang ran into this one specific challenge that needed a totally custom indexing solution. Now, Ang's primary motivation for this code update was highly practical. Just imagine you're trying to read these massive Chinese novels in PDF format. We're talking epic, sprawling stories here. When you're dealing with that kind of scale, you absolutely need a way to easily cross-reference specific topics, or maybe more importantly, you need to rapidly locate the exact pages where a specific character appears across a massive volume of text. Because without a proper index, keeping track of all those narrative threads in a 1,000-page PDF, it's nearly impossible. So that's the real-world problem this Haskell code is trying to solve. To pull off this dynamic indexing, Ang had to figure out exactly where to inject the new logic into the application's pipeline. The architecture actually relies on intercepting the text right at the raw parse token stage. This happens directly after the text goes through a custom parser, but, and this is crucial, right before it gets handed off to Pandoc's internal abstract syntax tree, or AST. By stepping in at this exact middle stage, the code can manipulate the raw elements of the document. That way, it injects the necessary indexing markers before Pandoc finalizes the whole structure. Okay, so with the interception point chosen right before the AST handoff, the code update kicks off by bringing in the exact right tools. Ang updates the file to import the replace function, and that's from the data.text.lazy library. Now, in the context of parsing massive novels, utilizing lazy text processing in Haskell is an incredibly smart move. Pulling in this specific replace function gives the program the exact mechanism it needs to systematically swap out standard text for our specially indexed keywords. Let's break down the apply Typst indexing function. What's really cool here is how it elegantly pattern matches its inputs. It makes sure this text replacement doesn't just happen blindly across all files, right? It deliberately targets only PDF and Typst export formats. Then it looks at the document's metadata to extract the keywords we want. From there, it maps a transformation over the document's tokens, finds paragraphs of text, and systematically replaces those extracted keywords with custom Typst markup. It's just a super clean, logical flow bridging the gap between raw text and a highly functional, searchable PDF. So, the code logically works perfectly for applying that custom Typst markup. The logic is completely sound. But when we remember the initial motivation here, that the target is a massive volume of text, like a gigantic epic novel, we have to stop and ask, how does this search and replace method actually perform when pushed to the absolute limit? I mean, does it scale? Well, here's the fatal flaw in the current version of the code. Ang openly admits there's a major performance bottleneck. During the search and replace process, the program is forced to repeatedly generate the keywords for every single loop of a paragraph token. Think about that for a second. If your novel has thousands upon thousands of paragraphs, the program is recalculating the keyword list every single time it looks at a new block of text. For a short article, you'd never even notice. But for an epic novel, you're essentially turning your CPU into a space heater. This repetitive processing creates a really severe performance impact. So the crucial takeaway here is that while the indexing theoretically works, and the goal of mapping character appearances is totally within reach, this brute force text replacement just isn't scalable yet. It perfectly highlights that classic developer journey, doesn't it? Making it work and then making it fast. We're kind of left hanging until Ang's next update to see exactly how this paragraph looping bottleneck gets refactored and conquered. And it leaves us with a fascinating question to ponder for your own projects. How often do we settle for code that works perfectly in theory, only to discover that the sheer scale of the real world completely breaks our architecture?